morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn about standing waves. Now, from this, we are going to get one of the mathematical equation for this standing waves. That term is called as standing wave ratio, and where that standing wave ratio is of two types: voltage standing wave ratio, simply we'll call it as VSWR, and followed by current standing wave ratio as CSWR. Right? So to get that standing wave ratio, nothing but VSWR, and the notation for that is represented with the small s. So to derive that, we will first discuss about how the normal incidence at a plane conducting boundary case, how the incident wave is completely reflected back to uh, the same medium, means there is no presence of transmitted wave, how the incident and reflected waves are travel or moving in that particular medium. Depending upon that, we are going to derive the equation called voltage standing wave ratio. Right? Normal incidence at a plane conducting boundary. This topic we are going to learn in this particular lecture. So, in the previous lecture, we have learned about normal incidence at a plane dielectric boundary. So, basically, there are two types of incidences that occur. One is normal incidence, and the second one is oblique incidence. Normal incidence and oblique incidence. So, in the normal and oblique incidences case, we will discuss two cases as normal incidence at a plane dielectric boundary and normal incidence at a plane conducting boundary. Right? Similarly, in the oblique incidence case also, we'll have two different cases as oblique incidence at a plane dielectric boundary and oblique incidence at a plane conducting boundary. So the first case already we have analyzed, that is normal incidence at a plane dielectric boundary. There we have considered two medium or media or both are a dielectric medium only. So for that dielectric medium, there we are assuming for that sigma is equal to 0, and now here in this lecture we will learn about normal incidence at a plane conducting boundary. Right? So to derive the here also we are going to derive two coefficients called, one is tau and next one is gamma, where tau is also known as transmission coefficient and gamma is said to be reflection coefficient. Right? So to derive that two coefficients, transmission coefficient and reflection coefficient, here the second case of normal incidence we have discussed is here is a normal incidence at a plane conducting boundary. Right? So in this we will consider the two media, means here also the interface or the boundary is located at z is equal to 0. Below z is equal to 0 we have medium 1, and above z equal to 0 means z is greater than 0 case we have another medium called medium 2. And the characteristic parameters are sigma 1, epsilon 1, mu 1 and eta 1. Similarly for medium 2, the characteristic parameters are sigma 2, epsilon 2, mu 2 and eta 2. Sigma is represented as the conductivity of that medium, and epsilon, mu are respectively permittivity of that medium and permeability of the medium, followed by eta is given by intrinsic impedance of that medium 1 and medium 2. Right? So these are the two characteristic parameters of the medium 1 and medium 2. That it means when the incident wave strikes the boundary, or when the incident wave touches the boundary, part of this incident wave, let it be this is EI or HI, means electric field intensity and magnetic field intensity vectors of the incident wave. Right? So when the incident wave strikes the boundary, where this boundary or interface which is locating at z is equal to 0, and in the medium 1 we have region is defined here, z is less than 0, and above means in the medium 2 we have the condition that is z is greater than 0, right? So to derive the conditions is for normal incidence at a plane conducting boundary. Here, the two medium means one of the medium is to be assumed as a dielectric medium, means let it be the dielectric medium, means medium 1 is considered to be dielectric medium, and medium 2 is to be conducting medium, right? So dielectric medium and conducting medium. So for the dielectric medium, sigma is to be assumed as 0. For the conducting medium, the sigma is assumed as infinite, right? Depending upon that conductivity, both the mediums are defined as dielectric medium and conducting medium, right? So the three characteristic parameters are epsilon 1, mu 1, eta 1, epsilon 2, mu 2, eta 2, right? As we know that. So firstly, now to evaluate the transmission coefficient tau and the reflection coefficient gamma, we need to know the what are the field components which are exist in the medium 1 and medium 2, right? So when the incident wave strikes the boundary, part of this incident wave is reflected back to the same medium, that is ER or HR we are supposed to represent, and part of this is transmitted to the next medium, that is represented with ET or HT, right? So when the incident wave means, when the incident wave is a combination of reflected as well as the transmitted wave, right? Hence, from this means when the incident wave strikes the boundary, part of the incident wave is reflected back to the same medium, part of the incident wave is transmitted to the next medium. Hence, if we observe in the medium 1, we have two waves, that is, one is the incident wave and another one is reflected wave. Similarly, if we observe here, in the medium 2, we have only the transmitted wave, let it be ET or HT. As we know that EI, HI, ER, HR and ET, HT are the electric and magnetic field intensities of the incident, reflected and transmitted waves respectively. Okay. So depending upon that, if you are going to derive the equation for transmission coefficient tau and the reflection coefficient gamma, we need to use the two boundary conditions between two dielectric medium. As we know that the dielectric medium boundary conditions, the first one is given by E1t equal to E2t and another one is D1n equal to D2n, right? If the charge region is to be assumed as charge free region, if rho s is equal to 0, the boundary condition is given by D1n is equal to D2n. Okay. Then the first boundary condition we have considered is E1t equal to E2t, right? Now depending upon this boundary condition and the field component which is exist in the medium 1 and medium 2, as we have got E1 is nothing but EI plus ER and E2 is nothing but ET only. Similar decomposition can be done for H also. H1 is nothing but HI plus HR and H2 is nothing but HT, right? So this is the way, if you consider the field components which are present in the medium 1 and medium 2, then the similar analysis what we have learned for the normal incidence at a plane dielectric boundary, here also means depending upon that we have got this one, transmission coefficient tau equal to, it is the ratio of transmitted electric field intensity vector related to the transmitted wave to the incident wave, that is ET by EI, which is given by here 2 eta 2 by eta 1 plus eta 2, right? Similarly, reflection coefficient gamma is given by, it is the ratio of reflected wave field strength to the incident wave field strength, and it is given by eta 2 minus eta 1 by eta 1 plus eta 2, right? So these two equations already we have derived in the case of normal incidence at a plane dielectric boundary. So the similar procedure, how we have evaluated, how we have considered the field components, everything is similar to that of normal incidence at a plane dielectric boundary. But Here, one of the medium we have considered is conducting boundary. So, see, a uniform plane wave striking the interface between the two media means the interface is which is separating between two media, where medium 1 is to be assumed as dielectric medium and medium 2 is to be assumed as conducting medium. Right? So, for the dielectric medium, sigma is assumed as 0, and for a conducting medium, sigma is equal to infinite. Right? So, where medium 1 is perfect dielectric. Perfect dielectric is also called as lossless dielectric. Right? Why it is lossless dielectric? Already we have studied in the case of wave propagation in characteristics of perfect dielectric medium or lossless dielectric medium. As sigma equal to 0, attenuation constant alpha 0. If alpha 0 means there is no attenuation, there is no loss in the signal. Hence, perfect dielectric medium is also called as lossless dielectric medium. And here, the normal incidence at a plane conducting boundary case, we have considered the first medium one is perfect dielectric medium and medium 2 is perfect conductor medium. So, for a perfect conductor, we have considered means the ideal value of the conductivity is given by here sigma equal to infinity. Right? As sigma equal to infinity, what is the value of E? As we know that J equal to sigma into E. What is this J in this relation? This is also called as point form of Ohm's law, and it is given by J equal to sigma into E, that is from conduction current density. The J is said to be conduction current density and it is given by sigma into E. Right? So now from this, if you want to write the equation for E, that is J by sigma. Right? So if you substitute the sigma by infinity in this case, means for a medium 2, we have assumed the sigma equal to infinity. Right? So if we substitute the sigma by infinity, then J by infinity gives us 0. Right? So E equal to 0. So that is the reason we have considered for a medium 2, eta 2 equal to 0 being a perfect conductor. Right? So if a medium 2 equal to, for a medium 2 to be considered as a conducting medium, E equal to 0 means what is there in the medium 2? ET or HT. Right? So transmitted wave field strength or instant electric field intensity vector of a transmitted wave as well as the magnetic field intensity vector of as HT. Right? So if ET equal to 0, means there is no transmitted wave. There is no transmitted wave means whatever the wave which is incidences the boundary or strikes the boundary, touches the boundary, the total wave is to be reflected back to the same medium. Right? So JC equal to sigma into E. According to that, the relation for E is obtained as J by sigma. If you substitute sigma by infinity, E equal to 0 in the case of medium 2 as to be considered as perfect conductor. Right? So, now from that, as we know that transmission coefficient tau equal to, it is the ratio of ET by EI equal to, right, 2 eta 2 by eta 1 plus eta 2. Right? Where eta 1 is said to be intrinsic impedance of the medium 1, eta 2 is said to be intrinsic impedance of the medium 2. As we know that eta 1 is related to dielectric medium and eta 2 is considered for the conducting medium. Right? So for a dielectric medium, sigma equal to 0. For a conducting medium, sigma equal to infinity. Right? So depending upon this, as eta 2 equal to, as we know that eta is in general, it is defined as it is the ratio of electric field strength vector E to the magnetic field strength vector as H. Right? So eta equal to E by H. Now, if you are assuming sigma equal to 0 for conducting medium, now what is the value of E? Just now we have seen E equal to J by sigma. This is from according to J equal to sigma into E. Now, if you substitute sigma by infinity, then E value is equal to 0. So, from this eta 2 equal to that is given by here Et by Ht. Why? Because in the medium 2, we have the transmitted wave, let it be, notations are given by Et by Ht. Right? So if E equal to 0, then Et becomes 0, hence eta 2 equal to 0. Right? Intrinsic impedance of the medium 2 for a conducting medium value is given by 0. Right? So if we substitute this eta 2 by 0 here, no, then tau equal to Et by Ei equal to 2 eta 2 means 0. Then transmission coefficient tau for the normal incidence at a plane conducting boundary case is 0. Right? Means there is no transmitted wave. Okay? Entire incident wave is reflected back to the same medium. Right? Similar to that, next coefficient called gamma. And this gamma is given by is the ratio of reflected wave field strength to the incident wave field strength. Gamma equal to ER by EA equal to, what is that formula we have got in the normal incidence at a plane dielectric boundary case? That is given by here eta 2 minus eta 1 by eta 1 plus eta 2. Right? So where eta 1 is known as intrinsic impedance of the dielectric medium, eta 2 is intrinsic impedance of the conducting medium. Right? So as we know that according to that analysis, E equal to 0 for the medium 2 and that 2 that is conducting medium. Means if we substitute eta 2 by 0 in this case, then minus eta 1 means 0 minus eta 1 by 0 plus eta 1 which is equal to minus eta 1 by eta 1, both gets cancelled, resultant will be equal to 1. Means gamma equal to ER by EI equal to minus 1. Means from this relation we can say that ER is equal to minus EI or EI equal to minus ER. Right? So from this we can say that at Z is equal to 0, interface is existing, and when the incident wave touches the boundary, this is EI or HI, then the total wave will be reflected back to the same medium. Means the notations are given by here ER or HR. Okay. Then, so EI equal to means if you observe the directions of these two are moving in opposite directions. Means at Z is equal to 0, we have two traveling waves, and at Z greater than 0 case, there is no transmitted wave. Eta 1 and here it is eta 2. Eta 2 equal to 0 for the conducting medium. Right? So EI equal to minus ER. Okay? Or modulus of gamma equal to, suppose if you consider gamma equal to ER by equal to minus 1, then ER equal to minus EI or EI equal to minus ER depending upon these two waves. Right? Or suppose if we consider modulus of gamma equal to, what is that? We have ER by EI equal to 1. Means ER is equal to EI only when we consider magnitude of the reflection coefficient. Okay, so keep in mind that sometimes we use in place of ER by, means ER is equal to modulus of gamma into EI, or sometimes if you substitute, if you write the equation for EI, then it becomes ER by modulus of gamma. If you didn't consider what the magnitude of this reflection coefficient, then EI and ER are opposite to each other. Right? So normal incidence at a plane conducting boundary case, we are assuming for the medium 1 is dielectric medium and medium 2 is to be conducting medium, as we know that for a perfect conductor, sigma equal to infinity, as sigma equal to infinity, there is no electric field present in that conducting medium. Right? So depending upon that, intrinsic impedance of that conducting medium eta 2 equal to 0, depending upon that, transmission coefficient tau is equal to 0 and the reflection coefficient gamma equal to minus 1. Right? So depending upon these two relations, there exist, means in the medium 1 there exist standing waves. Nothing but. What are standing waves? What do you mean by standing wave? What it consists of? How those standing waves are to be formed? Right? So standing waves also called as stationary waves. There is no movement in that particular wave. Hence, that standing wave is also called as stationary wave, right? So, standing waves are also called as stationary waves and combination of two waves moving in opposite directions, each having the same amplitude and frequency, right? Each are having same amplitudes and frequencies, but the moment or the direction in which they are moving is different, right? So, standing waves are the waves consisting of two traveling waves. Two are moving in two opposite directions, but the amplitude and the frequency of having both the waves are same, right? So, the phenomenon is the result of interference. So, that combination of two waves or the process is said to be here interference of the waves. That is, when waves are superimposed, one is superimposed on the another, their energies are either added together or cancelled together, right? So, cancel out to the each and every. So, this is the phenomena is called standing waves. Now, from this, we are going to derive voltage standing wave ratio. Simply, we'll call it as VSWR. Okay. Now, standing waves are nothing but it consists of two traveling waves. One is incident wave and the other is reflected wave. Instant wave field strength is given by EI or HI. Reflected is given by ER or HR. Okay. So, standing waves are nothing but standing waves are the waves. It consists of two traveling waves. One is instant wave and the other will be reflected. And those are does not travel. Hence, the standing waves are also called as stationary waves. Stationary waves. Okay. So, both the waves have same amplitudes, but the directions in which they propagate are different. Here, moving direction is different, but the amplitudes in which they are having are same, right? So next, now to write the mathematical equation for the standing waves. Let the standing wave in medium 1 is denoted with E1S. E1 is the notation for electric field which is present in the medium 1 and S is for standing wave, right? So let the standing wave in medium 1 is denoted with E1S. Why we have considered here E1S only? Why? Because in the normal incidence at a plane conducting boundary case, we are assuming in the medium 1 is to be perfect dielectric medium and medium 2 is medium 1 and this is medium 2. Here medium 2 is to be assumed as perfect conducting medium, right? So, two traveling waves which are existing in dielectric medium only. Hence, the dielectric medium is considered for the medium 1. Hence, the notation is given by here E1S. And E1S is equal to what it consists of? Two traveling waves, two moving waves. What are those two? EI, incident wave field strength, and reflected wave field strength. Incident wave and reflected wave. So, E1S is equal to EI plus ER, which is equal to. So, along with the magnitudes, suppose if you want to write the propagation direction also. So, consider here EI means EI into e power minus gamma 1z plus ER into e power gamma 1z into AX. Initially, we are assuming in the case of uniform plane waves or electromagnetic waves case, we have assumed always this electric field lies along the x direction. That's why the unit direction is considered AX. And for the incident wave, that is magnitude is represented as EI, and for reflected it is ER. And the propagation directions are given by e power minus gamma 1 into z, e power gamma 1 into z. Two are moving in two opposite directions, no? That's why minus gamma 1z plus gamma 1z, right? So, minus gamma 1z resembles forward direction wave and plus gamma 1z resembles backward direction wave. Z is the propagation direction where gamma 1 is represented as propagation constant. As we know that propagation constant gamma is nothing but it is a combination of attenuation constant alpha and the phase constant beta, where alpha is always real term and beta is always imaginary term, right? Depending upon this, E1s is given by EA plus ER, which is equal to EI into e power minus gamma 1z plus ER into e power gamma 1z, along with the unit vector direction is AX. Right. So from the conducting medium, just now we have seen that reflection coefficient gamma is nothing but it is the ratio of reflected wave field strength to the incident wave field strength and is equal to -1. This already we have analyzed, that is reflection coefficient gamma equal to eta 2 minus eta 1 by eta 1 plus eta 2. If we substitute this eta 2 by 0 in both the cases, then we are going to get minus eta 1 by eta 1 gets cancelled. -1 is the result, right? From that, gamma equal to ER by EI equal to -1. Okay? Now, next, for medium 1, sigma equal to 0. Why? Because for medium 1 means which medium we have considered? Dielectric medium. So for the dielectric medium, or for a perfect dielectric medium, for a lossless dielectric medium, we have assumed that conductivity value, ideal value of that medium, conductivity is equal to 0, right? So for medium 1, sigma is to be assumed as 0. Then as we know that gamma 1 equal to alpha plus j beta 1. Just now we have seen propagation constant gamma constitute attenuation constant alpha and the phase constant beta. So for a medium 1, hence it is gamma 1 equal to alpha 1 plus j beta 1, where alpha 1 is equal to 0. Why? Because this is the medium, dielectric medium, right? So insulating medium, dielectric medium, hence alpha sigma equal to 0, then alpha equal to 0, right? Why? Because this analysis already we have analyzed, that is gamma is nothing but alpha plus j beta equal to j omega mu along with the propagation characteristics. That equation is given by, mathematically we can write j omega mu into sigma plus j omega epsilon root over, right? Now from this, if we substitute for a dielectric medium, sigma is equal to 0, then j omega mu into j omega epsilon is left out. Now from this, j omega into root over mu epsilon, right? So gamma equal to alpha plus j beta equal to j omega root over mu epsilon. So there is no real term. What is that real term we have considered? Attenuation constant as alpha, right? So if alpha equal to 0, beta equal to omega root over, means from these two equations, alpha equal to 0, beta equal to omega root over mu epsilon. Okay, now from that analysis, means gamma 1 is equal to alpha 1 plus j beta 1, where alpha 1 equal to 0 for sigma 1 is equal to 0. We are talking about medium 1, hence all the notations are represented with 1 only, right? Gamma 1 equal to alpha 1 plus j beta 1, where alpha 1 equal to 0 for sigma 1 is equal to 0. Now if we consider here alpha 1 by 0, then gamma 1 is replaced by j beta 1. So previously what we have written, E1 is equal to EI plus ER equal to EI into e power minus gamma 1z plus ER into e power gamma 1z. Now we are replacing gamma 1 by j beta 1, right? So EI into e power minus j beta 1z minus EI into e power j beta 1z into AX. Why it is minus? Just now we have seen that reflection coefficient gamma equal to is the ratio of reflected wave field strength to the incident wave field strength according to the perfect conducting medium. Then eta 2 equal to, if we substitute 0, then gamma becomes -1. From these two, ER is equal to minus EI. Okay. Now from the previous equation, what is the previous equation? We have written E1s is equal to EI into e power gamma 1z plus ER into e power minus gamma 1z, that is plus gamma 1z. Now we are replacing ER by minus EI and gamma 1z by z beta 1. Hence E1s is equal to EI into e power minus z beta 1z minus EI into e power z beta 1z into vector direction as x. Okay. Now if you take EI as common, then E1s is equal to, so if you simplify, in order to write this function in the sinusoidal functions and exponential functions, we just considered means from this E1S equation. E1S is equal to, if you take EI as common from this, if you take EI as common, then e power minus j beta 1z minus e power j beta 1z into AX, right? To write this one on the complex variables like cosine function and sine functions, we are rationalizing this one with respect to the 2j. Then 2j into EI into, if you take negative as common here, then e power j beta 1z minus e power minus j beta 1z by 2j into AX. See, if you multiply this minus with the internal function, then minus into plus becomes minus this thing, and minus into minus becomes plus this one. Okay, then by 2j. If you cancel these 2j and this 2j, this becomes the previous statement only. Okay, then E1S is equal to minus 2j into EI e power j beta 1z minus e power minus j beta 1z by 2j into AX. Okay, then so E1S is equal to, this is the statement we have got. Now E1S is equal to minus 2j into EI sine beta 1z AX. According to Euler's function, then we have written here e power j theta means sine theta formula is as e power j theta minus e power minus j theta by 2j. Then this is the function for sine theta. Suppose if you want to write for the cosine, cos theta equal to e power j theta plus e power minus j theta by 2. Right? So hence it becomes E1S is equal to minus 2j into EI sine beta 1z into AX. Okay. Now this is the standing wave equation in the medium one, that is including the sinusoidal function. Right. So the field in the medium one. But field in the medium one means E1 is equal to, field component means we have to express that in the form of magnitude function. Then E1 is equal to real part of E1S into e power j omega t. Why we have multiplied this one with e power j omega t means in the previous equation we have got imaginary function. To get it as a scalar one, we need to multiply again it with imaginary. Then imaginary into imaginary becomes, it is a scalar one. So E1 is to be considered as the real part of E1S into e power j omega t. Right? So e power j omega t means, what is the formula? E power j omega t equal to, how are you going to write this one function? Sorry, for sine omega t function, sine omega t equal to e power j omega t minus e power minus j omega t by 2j. Okay, so if you write like that, then 2 into EI. Already in the previous statement we have the real term as, imaginary term as j. So that j into j becomes j square value is minus, and previously we have that negative term. So that negative term is eliminated by multiplying with imaginary, right? So 2 into EI sine beta 1z sine omega t into AX. Now if you multiply this one, this case also we have to consider real part of that function. Then only we'll get magnitude. Okay. So E1 is equal to 2 EI sine beta 1z sine omega t into AX. Okay. Then from this electric field intensity vector in the medium one, we will write the magnitude function for the magnetic field intensity vector. As we know that intrinsic impedance eta is equal to, it is the ratio of E to H. From this, if you want to write the equation for E, then it is multiplied with eta and H. Or if you want to write the equation for H, then it is considered as E by eta. Right? To write the equation for H, then H1 is equal to 2 into, already EI is there. Right? So EI by eta 1. Right? If you multiply these two, then it becomes 2EI. Right? So 2 EI by eta 1 cos beta 1z cos omega t into AY. Right? So this is a imaginary function, this is the real function. Or from the analysis of electromagnetic wave equation case also, we have considered if the electric field is located lies on the x-axis and the magnetic field is to be aligned on the y-axis, like that we have assumed, and the propagation direction is in the z direction. Okay, depending upon that, h1 can be written as 2ei by eta 1 cos beta 1 z cos omega t into ay. Okay, then if beta 1z is equal to n pi, consider here cos n pi. Suppose n is ranging from n equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, plus and so on, it varies. Then from that means if beta 1z is equal to n pi. Now from that z is equal to n pi by beta 1. But according to beta 1 means what is that phase constant beta is given by 2 pi by lambda 1, or in general wavelength lambda can be defined as 2 pi by beta, right? Wavelength of that medium is given by here 2 pi by beta. Beta is nothing but here phase constant, right? But beta 1 is equal to 2 pi by lambda 1, right? So in place of beta 1, if we substitute this relation 2 pi by lambda 1, then it becomes n pi by 2 pi by lambda 1. Now from this pi gets cancelled, then z is equal to n into lambda 1 by 2. So if we substitute z, the propagation direction z by n into lambda 1 by 2. See, after writing this E1 and H1, the field components which are present in the medium 1, E1 and H1, we will consider. Means if beta 1z is equal to n pi, beta 1z value ranges from n pi value, n coefficients, where n is ranging from 0 to like this, then z is given by here n pi by beta 1, and beta 1 value we know that from the wavelength equation lambda equal to 2 pi by beta, then z can be obtained as n into lambda 1 by 2, right? So, and representation of instantaneous values of the total electric field at t equal to lambda 1 by 2 in the medium 1. Why we have considered here lambda 1 by 2? The z direction is given by n into lambda 1 by 2, no? If you consider, suppose n is equal to 1, then t equal to lambda 1 by 2. So, if substitute n by 2, so lambda 1. If you substitute n by 3 like that, the t values are to be ranging, right? The magnitude of the magnetic field is maximum at the positions where the electric field is 0. Okay, so depending upon that, the waves or standing waves are drawn like this. If you observe, electric field intensity vector E and the magnetic field intensity vector H are orthogonal to each other, right? For a perfect conductor and for a perfect dielectric medium. See, at different values of x, at different values of lambda, these two are how the phases are to be changing. We are observed. You have to observe from this figure. Okay. See, these lines are represented, blue lines are represented as magnetic field intensity vector lines, and the E are to be pink lines are represented with electric field intensities, right? If you observe those two are differed by 90 degrees phase. Hence, E and H are orthogonal to each other, right? Then, to get the standing wave ratio equation, a uniform plane wave traveling in a lossless medium. Lossless means perfect dielectric medium. It gets reflected back by the perfect conductor, results in which a standing wave is to be generated. Means total incident wave is reflected back to the same medium. There is no transmitted wave present in the medium too. Hence, the combination of two waves are said to be here standing waves. Those are also called as stationary waves. Then the total field in the medium 1 along with the standing wave. So, E1s is given by EI plus ER. As we know that previously how we have considered the same equation, EI, the complete equation means along with the magnitude phase functions, if you write EI into e power minus gamma 1z plus ER into e power gamma 1z. The reflection coefficient from this, gamma equal to ER by EI, modulus of gamma. Then ER equal to modulus of gamma into EI. Then from this, if we substitute ER by in terms of EI, means E1s is equal to EI into e power minus j beta 1z, then modulus of gamma into EI into e power j beta 1z. Previously, we have considered gamma equal to ER by EI equal to minus 1. Now we have considered modulus of gamma, means magnitude we have considered, then ER by EI equal to 1, then it becomes ER equal to EI only. Hence, ER is replaced by modulus of gamma into EI in this particular function. Then, the reflection coefficient in phasor form. So, gamma, if you want to express that in terms of magnitude and phase, then gamma equal to modulus of gamma into e power j 5. Then E1s is equal to. Now, if you substitute gamma by that function, modulus of gamma e power j beta 1z plus 5, right? Previously, we have e power j beta 1z only. Now, it is multiplied with e power j 5. So, this is the formula a power m into a power n. Then the formula becomes a power m plus n. So, e power j beta 1z plus 5 into ei. If you take ei as common between 2, then these two. Then E1s maximum equal to, when you are going to get the maximum value, if that cosine function or beta 1z 5 function becomes 0 case, then E1s maximum equal to 1 plus modulus of gamma into EI, right? Then when you are going to get minimum value of that one, means if you consider imaginary functions, right? So E1s minimum equal to 1 minus modulus of gamma into EI. Right? Understood from this E1s maximum and E1s minimum. So E1s maximum value is to be obtained for the even function and E1s minimum value is to be obtained for the odd functions. Right? So even function is an example for cosine signal and odd function means it is example is given by here sinusoidal functions. Right? So E1s maximum equal to 1 plus modulus of gamma into EI and E1s minimum equal to 1 minus modulus of gamma into EI, right? Now, to get the equation for standing wave. Now, standing wave ratio is defined as the ratio of maximum to minimum amplitudes of the voltage. Hence, it is given by VSWR, voltage standing wave ratio. And it is denoted with S equal to E1s maximum by E1s minimum. What is that E1s maximum here? 1 plus modulus of gamma into EI by E1s minimum is 1 minus modulus of gamma into EI. Right? So, if these two gets cancelled, 1 plus modulus of gamma by 1 minus modulus of gamma is the value is to be obtained for voltage standing wave ratio. Right? So, S is equal to 1 plus gamma by 1 minus gamma means from this we want to write the equation for this modulus of gamma. So, to write the modulus of gamma, S into 1 minus modulus of gamma equal to 1 plus modulus of gamma. Now, S minus S into modulus of gamma equal to 1 plus mod gamma. Now, separate this reflection coefficient and S functions. So, S minus 1 equal to S into modulus of gamma plus gamma, right? S minus 1 is equal to, if you take mod gamma as common, S plus 1 is to be obtained. Now from this, mod gamma equal to S minus 1 by S plus 1. Okay, so standing wave ratio, that is VSWR, S is denoted with S is equal to E1s maximum by E1s minimum and it is given by 1 plus modulus of gamma by 1 minus gamma and the reflection coefficient gamma equal to S minus 1 by S plus 1. Now from these two relations means modulus of gamma equal to S minus 1 by S plus 1 and standing wave ratio S is equal to 1 plus mod gamma by 1 minus mod gamma. Depending upon these two, reflection coefficient gamma and the standing wave ratio S, we will write the ranges of these two factors, right? Suppose if we substitute gamma by, in general previously from the normal incidence at a plane dielectric case, we have got gamma is ranging from 0 to 1, right? So first, if you substitute this gamma by 0 first. So 0 equal to s minus 1 by s plus 1. Now from this, s is equal to 1. Okay. Next, if you substitute 1, means s minus 1 by s plus 1 is equal to 1. S plus 1 is equal to s plus 1 equal to s minus 1. Or if you take s as common, then the value is to be ranging from both. Sorry. If gamma equal to 0, s minus 1 by s plus 1 is equal to, if we substitute gamma by 0, s equal to 1, and ranging from where s value 1 to infinity. And similarly, if we substitute s by 0, gamma is ranging from 0 to 1, like that, right? So the ranges of this gamma and s are given by gamma is ranging from 0 to 1, and s is ranging from 1 to infinity. Okay, so reflection coefficient gamma and the standing wave ratio, or how these two are interrelated based upon the standing waves we have learned. So what do you mean by standing wave? Standing waves are also called as stationary waves. These are forms or combination of two traveling waves, means incident wave and reflected waves is said to be here standing waves, and it is denoted with the factor standing wave ratio is denoted with S, and the range of that will be ranging from 1 to infinity. Okay, so what we have learned in this particular lecture is, from the normal incidence at a plane conducting boundary, we have derived the equation for voltage standing wave ratio. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.